Hello, everyone, and welcome to our Earth Engine introductory session, coming to you this year in our virtual distributed summit. We're all learning what life on an interconnected planet can throw at us, and also learning how interconnected our collaborations can be. I truly hope you're finding ways to thrive this year. I'm Joel Conkling, Product Manager for Earth Engine.
Hello, everyone. I'm David Gibson, the Technical Lead for Earth Engine. We would like to tell you a little bit today about Earth Engine, where it's come from and where it's going, with particular mentions of the new features that we've been working on recently. We're also excited to welcome a special guest from the group on Earth observations.
Hi, I'm Stephen Ramage from GEO, the group on Earth observations in Geneva, Switzerland.
We'll bring Stephen back later in the presentation. Earth Engine is a cloud service for petabyte scale analysis of geospatial data with a vast archive of satellite imagery and other data sets, up to 35 petabytes now. And equally importantly, it has freely accessible computation capacity to do analysis at that scale. We manage the data in the computers so that you can focus on doing good science and translating that science into decision-making and action in the real world. It's been an amazing journey so far. And in fact, we're coming up on our 10th anniversary for Earth Engine this December. Ideas for Earth Engine really started to germinate as early as 2007, when the Google Earth Outreach Program was started, with the aim to tackle issues including environmental protection and global public health. Earth Engine itself was first announced in 2010 at the ICCC in Cancun, promising to support 10 million CPU hours per year of computation, and even mentioning the project that became Global Forest Watch. In 2014, we increased that to 50 million hours in the White House Climate Data Initiative. Then the code editor was launched in 2015, and we explained the system to the world in our 2017 remote sensing paper, and that's still the best citation to use in your own work. In recent years, we've focused on increasing our functionality and scale still further, enabling you to reach new audiences with EE apps, making the data catalog easily browsable, and starting to collaborate with Google Cloud systems, which let us increase scale and functionality in many ways. Along the way, our compute capacity has grown to the point where we're supporting 300 million compute hours per year. It's a big jump from the 10 million where we started. And in this time, our user base, you, has grown to over 200,000 signed up users, and the code editor in particular now has over 30,000 users active in any month. I think it's particularly impressive. The rate of publications has been nearly doubling every year. At this point in 2020, we are at 2,500 Google Scholar citations. Earth Engine apps have been growing at a similar rate, with over 10,000 published at this point. We've also introduced community tutorials so that everyone can contribute to our public documentation. For example, by providing specialized techniques for your research domain. With that, I'll hand it over to David.
Hi, a geological metaphor seemed appropriate at this stage because Earth Engine does consist of many layers, including the data catalog, the computation engine itself, tools and algorithms which drive that engine, and then visualization and publication tools which let you share your results. The Earth Engine data catalog is the basis for many Earth Engine analyses. It's a publicly accessible archive of analysis-ready data from several satellite providers, including the full Landsat archive from 1972 onwards, many data types from the Copernicus Sentinel program, including radar, optical, land color, and atmospheric data, and over 700 other data sets. As a couple of recent highlights, we've added the GOES 16 and 17 geosynchronous satellite feeds in a near real-time mode where the data is available within minutes. We've also run the Sentinel-2 cloud probability algorithm over the entire S2 archive to make cloud-free analysis easy. You can see the data catalog presentation for more details. In the layer above the data catalog, Earth Engine lets you ingest your own data in a variety of formats, including GeoTIFFs, shapefiles, CSV, and TF records for TensorFlow machine learning data. Newly arrived, we have a feature for instant ingestion of the cloud-optimized GeoTIFF format, which lets you use imagery that's stored in Google Cloud Storage without ingesting it into Earth Engine first. This is particularly valuable if you have lots of your own imagery to manage. You can see SciTalk for more details here. Now, once you have all the data you need, Earth Engine offers a powerful range of functionality for analyzing that data. Here's an illustration of the 3 major kinds of operations that Earth Engine can perform at scale. We have operations that transform images to derived images, ways to use geometry information to produce summary tables of data from images, and then operations that work on tables. Central to these processes are the reduction operations, such as reduce regions, which intersects the raster and the vector data to give statistics per region. We've been continuing to work to optimize these at scale because these are so very central to many analyses. For table operations, then there are map, reduce, and filter commands, as well as standard inner and outer joins to combine tables. I did mention TensorFlow. We have improved support for machine learning using both deep neural nets and statistical classifiers. In fact, we've upgraded our EE.classifiers to new versions based on the open source SMILE library. This includes random forest, naive Bayes, decision trees, or BART, and SVM classifiers. The new versions take the same parameters as before, but perform better and have new explain features too. So we encourage you to switch over. You can import and export data in TF record format to train TensorFlow models. And EE.model lets you use trained models directly in Earth Engine code. You can host models on Google's Cloud AI platform and run inference on imagery and on tabular data using predict properties. We've been actively improving the performance of these algorithms. You can see the talk on Dynamic World, in particular, where Chris will describe how we've built a global 10-meter land cover map. We've now covered the central elements of the data catalog and the compute engine. So how do you use these tools to investigate phenomena and develop new data products? There are really 3 levels of access here, and we're going to start in the middle at the surface of the Earth, if you like. Most people use Earth Engine for analysis by writing short programs in JavaScript or in Python. Working in Python, in familiar Python notebooks, lets you control large computations in the cloud and then integrate the results with popular Python libraries such as NumPy or TensorFlow again. You can also use visualization tools. Recently, we've worked with the DeckGL open source project to add very fast GPU-based rendering of Earth Engine data. Here's an example using a Python notebook. On the other hand, working in JavaScript in the code editor gives you a centralized workbench to manage your analyses. It has interactive access to features like the data catalog, data layers on the map, geometry drawing, online documentation, and also easy ways to save and to share your work. And the code editor also lets you publish apps. In this diagram, if you like, the atmosphere. These are no-code, interactive presentations of your results, which might be demos for stakeholders or tools for users of your data. Many of the features of the code editor are also available in apps. You can show layers on maps. You can use widgets to configure analyses and compare data. The geometry drawing tools are now also available in apps so that you can show pre-drawn geometries and build apps that let users input regions of interest. Here's an app which lets you pick regions to build a time-lapse animation of river flow. Apps can be restricted for cases where you have private or preliminary work to share with specific people. And we've also added handy URL parameter access to your scripts and apps, and a resize handler so that apps can adapt to phones or smaller screens. Lastly, you can check out the app creator for some compelling work to let you build interfaces without coding. For more details, you can see Michael and Karen's fun cooking class later in the summit. Now, if the code editor and apps are too high level for your needs, we can go deeper. You might possibly be integrating Earth Engine into a wider system, or you might need to manage a lot of data. The JavaScript and Python that you write uses our client libraries, and these in turn use the underlying REST API, which communicates with our servers. Now, the client libraries do make coding easier, but we've been working on this direct access layer to make a future-proof and standardized way for programmers to integrate across other Google products. So this under-the-hood access opens up new kinds of complex applications. You can see Arian and Daniel's talk for a gentle introduction to the REST API. The success and impact of Earth Engine depends on the work that our users and our partners do with our tools. Now, some of these partners are internal to Google. For example, we've been working with the Google Maps teams to add live wildfire maps based on the near real-time GOES imagery. You can see the details in Vanessa's talk linked here. We've also been partnering with Google's research and cloud AI platform teams to bring you EE.model functionality. And our ML work has led to a partnership with National Geographic to build what we're calling Dynamic World. It's an up-to-date global land cover classification using deep neural networks at 10-meter resolution, which is hugely useful for agriculture, biodiversity, and carbon monitoring. You can see this talk for more. I would now like to turn it over to Stephen to talk more about our newest work with partners. Welcome, Stephen.
Thanks, David. GEO is an intergovernmental partnership representing more than 110 UN member states. We work globally to help countries understand the value and usefulness of Earth observations for research, policy decision-making, and action. I've been developing our private sector engagement since I joined the GEO Secretariat in 2016, and with the arrival of Gilberto Camara as the new director in June 2018, we really pushed engagement in this area. It also helped that Gilberto was one of the early contributors and advisors on Google Earth Engine. So when Google offered to support us, we jumped to the opportunity to help our members and partners. We have now successfully awarded 32 projects internationally with technical support, i.e. capacity development help from EO Data Science in Australia. And I should also give a shout out to my colleague Doug Prout for leading this process. The goal of the program is to help measure the pulse of the planet. I was listening to Rebecca Moore earlier this week on the Big Enchilada, and she described the Google Earth Engine team as the IT department for the planet. So I'd like to think that our global community can use or benefit from this wonderful IT department. As well as assessing research excellence, impact, and project implementation, we wanted to comply with the global policy mandates that GEO follows. For example, the UN 2030 Agenda, the Convention on Biological Diversity, the Paris Agreement, the Sendai Framework for Disaster Risk Reduction. On the ambition side, we wanted to look at the potential for scalability or reproducibility for users around the world. I'd like to share some information about a couple of the many successful projects. However, first I'd like to acknowledge that KTH from Sweden will also be speaking at GEO for Good regarding their project from the joint programme, discussing environmental change monitoring with a focus on urbanisation and wildfire monitoring. The first project I want to talk about is Costa Rica. The awarded project is related to tackling deforestation with forest degradation and using Google Earth Engine. And this will be carried out by a team of experts led by Rafael Mong, who is the director of the National Centre of Geo-Environmental Information, SENIGA, and a member of the GEO community. Costa Rica has an amazing track record in climate action, and even the presidency of Costa Rica issued an official note saying that the country was satisfied with the grant Costa Rica received as part of this joint GEO and Google Earth Engine program. The second one I want to talk about is the United Nations Environment Programme, known as UNEP, working with the University of Edinburgh from my home country of Scotland. They're collaborating on an environmental and climate stress index called Strata. The main objective of this is to help end users rapidly understand where the convergence of environmental stressors is occurring around the planet, how and why the intensity of these hotspots is changing over time and space, and then where these hotspots could interact with other social and economic variables to impact livelihoods and increase the risk of fragility, social conflict, or migration. The project is starting with country-level prototypes in Haiti, Colombia, and Somalia, and scaling up the development regionally in the Horn of Africa, the Sahel, Latin America, and the Caribbean. Finally, moving on to a global prototype. One of the exciting aspects of the collaboration is that UNEP is already working with Google and GEO on the SDGs for water, and they're partnering with an award-winning startup called Earthblocks out of the University of Edinburgh. Earthblocks aims to simplify and broaden access to Google Earth Engine. From a policy perspective, this work will be embedded in what's known as the common country analysis, the CCA, including with the UN resident coordinator and UN country teams, and that's big. For the Geo for Good community, we're very happy to share all the information about the awards and obtain feedback, including any possible contribution to the ongoing projects, ideally being as inclusive as possible. This also includes bringing some of this work back into the Geo work programme. We're very happy with this collaboration and really look forward to successful delivery of these projects and to the global impact. So thanks again to Google and EO Data Science for this opportunity to drive the use of Earth observations globally.
Thank you, Stephen. That really is an amazing set of collaborations, and we're looking forward to discussions over the rest of the summit. And thank you, everyone, for joining us today, and enjoy the rest of the Geo for Good summit.
Thank you. Have a great summit.
Thanks.